This is the single supply classical bias arrangement for discrete circuits. The only difference between this and the previous technique is that we have a resistance Re in the emitter lead. We can redraw this circuit with its Thevenin equivalent. On this loop L on the bottom of your screen, we can write an equation. This equation comes out IE equals VBB minus VBE divided by RE plus RB divided by beta plus 1. We have used this equation. IB is equal to IE divided by beta plus 1. Now remember why we were biasing. We wanted to make IC insensitive to temperature and beta. However, since IC is related to IE by the formula IC equals alpha IE, we can also achieve this desired biasing by making IE insensitive to temperature and beta. So, looking at this equation again, we can achieve this if we impose two conditions. VBB should be much greater than VBE and RE should be much greater than RB divided by beta plus 1. In this way, IE will truly be insensitive to temperature and beta. Why? Because any changes, that is, any small changes in VBE will be swamped by the very large VBB. Similarly, any changes in beta are going to be swamped by the very large RE. However, there is a limit on how large VBB can be made. Look at this equation on your left. Since VCC is constant, if we increase VBB, the lower will be the sum of voltages across RC and the collector base junction VCB, these two places here. This is because all of these lie in this loop, L2. On the other hand, we also want the voltage across RC to be large in order to obtain high voltage gain and large signal swing. Remember the formula for gain, AV equals minus VRC over VT. We also want VCB to be large to provide a large signal swing in the negative direction as well, that is towards saturation. So, we need to come to a compromise. As a rule of thumb, one designs for VBB equals 1/3 VCC, VCB or VCE also 1/3 VCC, and VRC, that is IC multiplied by RC, also equals to 1/3 VCC. This is unless specified otherwise. Now the second condition here means that we want to make the base voltage independent of the value of beta and determined solely by the voltage divider. This will obviously be satisfied if the current in the divider, here on your top left, is made much larger than the base current. Typically, one selects R1 and R2 such that their current is in the range of IE to 0.1 IE. So how does this arrangement stabilizes IE and by extension IC? Consider for some reason the emitter current increases. This means the voltage drop across RE and thus VE will increase. Now as we just saw that the base voltage is determined solely by R1 and R2. So if these two are kept constant, the base voltage VB will also remain constant. Now since VE is increasing, VBE will decrease. Why? Because VE is subtracted from it. Now as we know that decreasing VBE will also decrease IC and by extension IE. And so this is how this biasing arrangement stabilizes your current. RE is said to provide negative feedback. Now to understand this better, let us look at an example. We are given VCC as 12 volts, beta is 100, IE equals 1 milliampere, and our job is to design the circuit. This means finding the appropriate values for RC, RE, R1 and R2. Now we start our design by first distributing the voltages as we had discussed. So VBB is 4 volts, VCB is also 4 volts, and ICRC is also 4 volts. So what is VB? Since VC is 12 minus 4, that is 8 volts, VB comes out to be 4 volts. We write an equation for VE. 4 minus VBE, and since we know the value of VBE, VE comes out to be 3.3 volts. We can calculate RE. This is 3.3 kilo ohms. Now remember what we talked about, that the voltage divider current would have a value between 0.1 IE and IE. So we select a value of 0.1 IE, and this comes out to be 0.1 milliampere. Neglecting the base current, we write two equations. Solving these simultaneously gives us R2 equals 40 kilo ohms and R1 equals 80 kilo ohms. Now since we have neglected the base current, there is going to be some error in our calculations. One way to check that is to recalculate IE. We put in the values in the equation for IE that we had found out at the start of the video, and find out that the value is IE equals 0.93 milliamperes. This is obviously a bit lower than the value of IE that we were hoping to establish. So how do we rectify this change? There are two ways to do it. First one is to reduce this value here. This is RE. And the second one is to reduce the value of the parallel combination here. That is, we change the value of R1 and R2. So let's see how the first one works. In the first one, we find the value of RE, that gives IE approximately equal to 1 milliampere. Use this equation and find that RE comes out to be 3 kilo ohms. Now in the second method, we change R1 and R2 to give us IE equals 1 milliampere. Again we use this equation. This gives us R1 equals 8 kilo ohms and R2 equals 4 kilo ohms. Now remember that RE does not have to be changed in the second method, and the first method R1 and R2 need not be changed. Now moving on to the rest of the circuit, we can find RC very easily. This comes out to be 4 kilo ohms, and we have used the value of alpha to be 1 as compared to 0.99. This is just for simplicity. And so with that, our design is complete. Now let's move on to other biasing techniques.